Each carbon have two.
Two. Yeah. Now I write one question and please tell me, have you here cis trans isomer or not? For example, if you have CH3, CH2, CH3. What about this molecule? No.
Now all different.
Open. So write separately. H and here you have Cl. Have you here at least one pair? No. H, CH3, Cl, CH2, CH3. You haven't here same groups. So you can't discuss here about cis trans isomers. But
this is H, we can.
yes, but you can discuss here about EZ isomers.
Yeah, because we have four
EZ
different.
isomers. Now, what means EZ isomers? Please, first of all, look here. You have four different groups. But you can't discuss about geometric isomers. But you can discuss about EZ isomers. Now, what it means? Divide this molecule. And first of all, look at this card. So, you have two substituents, CH3 and H. Which one has higher priority and which one? Yes. This is number 1. This is number 2. Now what about these two groups? This is number 1 and this is number 2. Now remember, if your same priority groups are on the one side of your plane, so you have Z, E isomer. It's E means at Gegen, it's from German word separately.
Gegen?
It's Gegen. Look, 1 and 1. They are on the opposite side. So it means that it's Gegen. So separately. It means separately. Now if you have another version like this. This one is E. Look, C, double bond, C. And Gegen. CH3, Cl, CH. It's the same. No. CH3 and H. Now what about this?
Yes, this is not.
This is number 1. This is number 1. This is number 2. This is number 2. So if your groups which have the same high priority or low priority on the one side of the plane, in the plane of your double bond, so you have Z, Susanna. Susanna means together. Susanna means together. So this one is Z. Suzhammer. So Z. This one is Z. This one is E. This one is Z. This one is E. Now if you have cyclopropane, as you remember, cyclopropane has planar molecule. Yeah, it's planar molecule. So in case of cyclopropane, you can discuss about cis trans isomers. For example, if you have dimethyl cyclopropane, and if your one methyl group is here and second one is here, so this one is trans.
Okay, it's okay.
If you have this version, CH3,
Cis.
this one is cis.
How we naming? Cis, iso.
Cis. 1,2 dimethyl cyclopropane or trans 1,2 dimethyl cyclopropane.
اقول لك جابر وزاد
مرشح اكتب عليه مرشح
1,2 yes 1,2 dimethyl cyclopropane, but in this case you have cis, in this case you have trans. Now tell me please, you have this version.
يلا رجعنا على
You have this version. This molecule.
ضحكت يا ضحكت منها.
For example, this one. Now let's discuss about all types of isomers. First of all, tell me please, have you here chiral carbon or not?
This cis.
Chiral carbon. No.
Chiral.
This is this one. Chiral carbon.
They
What
have
is
different.
chiral carbon?
They have different.
Four different substitutes. Have you here chiral carbon? No.
Yes, yes. The
Yes,
second.
Yes. This one is your chiral carbon.
three,
Okay,
four.
now look. 1, 2, 3, and this is together 4. So
Second
you
one.
can discuss about optical activity of this compound. Why? Because of here you have chiral carbon. Yes?
But we need the double one. We don't.
Just a moment.
Other
Look, you have how many types of configurational isomers? It's optical active compounds, enantiomers, diastereomers, where you need at least one carbon atom with 4 different substituents. Second one is cis-trans or geometric isomers. Here you always need a double bond and at least one pair of the same groups which are bonded to these carbons, but separately, with one and with second carbon, not together with one carbon. So in this case, I can discuss about optical activity of this molecule. So this molecule is optical active molecule. Yeah. Now what about geometric isomers? Look.
CH3 and H.
Now let's cycle double bond substitutes.
Yes, we can.
This is
Yes, you can. You can. Why? Because of this is your 2 carbons which are in the double
We
bond.
have H.
So H and H. Here you have same.
Cis.
CH3 and this group together.
This.
So this molecule has geometric isomers and has configurational isomers or enantiomers or diastereomers. Yes. Why? Because of here you have chiral carbon. Now what about this one? What about this one? Has this molecule geometric isomers or not? No. Why?
Yes, they are. But geometric.
Yes, this carbon.
Two H.
Two same HA. Now what about optical activity?
No. No H.
Look carefully.
Yes.
Yes,
We have 4 different.
Yes.
third one.
This carbon is chiral carbon. Look,
Yes.
right like this.
Let's open it there.
1, 2, 3, and 4. So you have 4 different substitutes. Now, what about once again in case of enantiomers? As you remember, they have same value of angle, rotation angle, but they have different direction. Yeah, if one rotates this polarized light to the left side, the second one rotate to the right side. If you take equimolar amount of these 2 enantiomers, for example, if you take 1 mole and 1 mole of both enantiomers, and if you prepare their mixture, so this mixture will be optically inactive. Why? Because of 1 enantiomer's action will be neutralized by second enantiomer's action. So if one rotates on the left side on the 20 degrees, second one rotates on the right side once again the second degree. So finally your mixture is optically inactive. So we call this mixture racematic mixture. Once again, racematic mixture is mixture which contains equimolar amount of 2 enantiomers, and they neutralize each other's action. But if you take diastereomers, in this case, in any case, you take equimolar amount of these 2 diastereomers or different amount of these diastereomers, your mixture will be optically active because of they have different angle of rotation, because they are diastereomers. Now what about molecule in which you have 2 chiral carbons, for example. But molecule is optically inactive. Look.
لازم تراسته.
Now look. In this case, they are mirror imaging of each other, so they are enantiomers of each other. Yeah, they are enantiomers of each other. So this. Now, how you have to determine the absolute configuration of a molecule where you have several chiral carbons? In this case, you have to use for each carbon this parallel angled or SIP system. Angled parallel or SIP system. It's abbreviation of the science. Now, first of all, let's discuss about this one. This is number 3. Don't look at this part.
The last one.
Number 3. This is number 1. This is number 2. Don't look at the lowest group's priority. 1, 2. So it's anti-clockwise.
Yes.
And because of your the lowest group on the vertical line, so you have to change S into R. So your first, this is first carbon, this is second, third, fourth carbon. Your second carbon's absolute configuration is R. So you have to write like this, 2R. 2 means that second carbon has R absolute configuration. Now what about this one? Once again, number 3, 2, 1. Don't look at this. 1, 2. So clockwise. It has to be R. And you have to change into R. So finally you have 2R, 3S. Now what about this one? No, it's mirror image of this one. Do you remember? These two enantiomers. One is R, second one have to be S. Now this is number 3, number 2,
This is number 2.
1, 2.
This is
Clockwise. So you have 2R and you have to change this into S. So you have 2S. And here 1, 2, and 3. Anti-clockwise.
3R.
And you have to change 3R. As you see, these two molecules are mirror imaging of each other. They are enantiomers, and their chiral carbon's absolute configuration is changed. 2R, 3S, 2S, 3R. Now what about optical activity of this molecule? Is this molecule optical active or not?
Because we don't trust any.
No. That's information. Only 2 words. Only 2 words. Guys. I know that it's a difficult part, but I won't explain everything today. Only 2 words. Only 2 words. Now look, this molecule have to be optical active. Yeah? Really, it have to be optical active. But because of through the molecule, you can pass symmetry plane. Look, this part is mirror imaging of this part. Like this. This part is mirror imaging of this part. So this molecule, this carbon's action is neutralized by this carbon section. And finally, your molecule is optically inactive. And we call this molecule mesophore. So once again, mesophore is stereoisomer where you have different position of substituents, but mesophore is optically inactive. Why? Because of one part of molecule is mirror imaging of second part's molecule. Yes, so now listen to me. It's chapter 3. Before.
We will repeat this one.
3.4.
اسمر القلم محمد.
كان معكم
Please write.
الحسين. هذا عقيل.
Except